Hi, my name is Clifton Rusboom, and I'm the CEO and founder of PocketLab. Thanks for joining our session today. What we're going to show in this session is me acting as an educator and working with a student, a freshman physics student, remotely to do an experiment where we model the discovery of exoplanets. And we're going to do a hands-on demonstration where I have equipment here in my house and the student doesn't have any equipment, but we can use PocketLab and our software PocketLab Notebook to do a pretty rich hands-on science experiment in the absence of having any equipment that we would normally have access to in our classroom or in a lab. To learn more, visit us at thepocketlab.com and see what we're doing to help in this remote and hybrid learning situation that we're in right now. PocketLab is a wireless sensor to gather data from the world around you. PocketLab connects with a single button to a tablet, smartphone, or computer and displays data in real time. In seconds, you can start learning about magnetic fields, acceleration, or temperature, and your data easily integrates with programs like Excel or Google Docs.
Being able to take a Nerf ball, cut it in half, slap the PocketLab inside of it, rubber band it together, and then kick it and videotape it was extremely powerful.
These girls spent the last 2 weeks learning computer programming. They're a select group chosen to experiment with PocketLab, a physics lab that allows them to expand their coding skills.
I thought it was going to be complicated, but it's actually pretty easy.
Naomi Franklin is 11 years old and about to go into 6th grade. She already has several career paths in mind.
Usually with earthquakes, we use accelerometers to kind of look about how stresses and strains are built up and how they release over time.
I can have my IEP students and my exceptionality students and gifted learners challenge with the use of PocketLab. So we build in your video tutorials, we link in things right through your website and have student produce amazing work within groups.
Lets you bring the concepts into the classroom and for students to learn about concepts in a way that's really different than reading about them in a book or taking a test on them. For example, one of my students said, I didn't really understand this effect you were talking about in class until I saw it at work in a sensor.
Can you introduce yourself?
I'm John Paul, and
what grade are you in?
I'm a 10th grader at Bellarmine.
We're live on Zoom, and we're using PocketLab Notebook for doing the science data collection and for taking us through our lesson. So I have a setup here that we're going to use for modeling planets orbiting around a sun and how we could discover distant planets. And I know you don't have any of this setup. Most people don't have a record player at home. So, John Paul, have you ever heard the term exoplanet?
I think I've heard it, but I'm not sure what it is.
Just take a guess. What do you think that term might mean?
Like a planet that's maybe far away.
Yeah, exactly. So it's a planet that's orbiting a star that's not in our solar system. So they're very distant, and we're interested in learning more about them. But they're typically difficult to discover and difficult to observe.
Maybe because you can't see them as well because they don't emit light.
Right. Yeah, they're only reflecting or blocking the light from nearby stars, and so they're many orders of magnitude dimmer than the stars that they're near. So if you point a telescope at them, it's clearly, you can clearly see the stars, but the planets that are nearby are very hard to depict. So what we are going to do is, we don't have an observatory handy for us right now, but we're going to try to create a model of how these things work. What do we use models for?
To replicate what's going on in the real world. I know a lot of models are much smaller than what's going on in real life. Like a model of a city, if you can put it all on a table versus, cities much larger.
Right. And in the case of our model that we're going to use, which is over here, the scaling is quite off. So here we have here our planet, and then this light bulb is going to be our sun or our star. And you can see they're not that different in size, but that's because of the materials that we have to make this nice and easy. So John Paul has a version of the PocketLab notebook activity open on his computer. He's got a student copy, and on the screen, in my screen recording, we have a version of, we have the teacher version, and I can see everything that John Paul sees. We're gonna take this simulation here, and we're gonna reproduce that here with like on our tabletop. So have you ever seen a record player? Have you ever used a record player?
I definitely have never used a record player before.
Okay. And then what we're going to do is we're going to collect data using PocketLab. And John Paul, I know you've seen this in person, the light sensor to collect data from this experiment. And I'll get the setup going, and then I'll share my screen. So if we're going to start to collect data from this experiment, how would you like me to set up either the light bulb or the planet or the PocketLab?
Well, you might want to put start out with putting the PocketLab like at a medium distance away from the light bulb, or the.
Okay.
So maybe a foot, or I'm not sure.
Okay.
I know that I can't see the angle quite.
Yeah.
Maybe a foot.
Yeah.
Away.
And do you see how the data is changing?
Oh yeah. Wow.
So, okay. So we can try a foot away. Okay. I'll try it on our slow speed.
Okay. And yeah, I can see that the data is definitely changing as that spins around.
Okay. So I'll start to record some data so that you have that later to analyze.
So it seems like every maybe every second or about so, the light intensity will just drop by a lot, by like 600 LUX.
Yeah, that's lux. That's a measurement of visible light. So I'll stop the data recording. And yeah, like you said, there's this periodic dip in the light intensity. So do you know what that term is? If you have something that happens regularly, like regular spacing, the time in between those events?
Maybe a cycle.
Yeah, a cycle. And the time in between events we normally call a period, which we would talk about in terms of time. So in this case, seconds. If you're looking at a planet, it could be days or years. And you can observe here, yeah, that period. Okay, so I'll save this, and then you'll have that to refer to later in the lab report.
Yeah, let's try like maybe doing it manually and like just doing it at like a really slow speed.
Okay. All right. So I'm gonna crank it over there, and I'll start recording some data for us to preserve. Can you see the planet? I know it's pretty bright. That light bulb's pretty bright. Now it's about to go behind the light bulb, and it's coming back around in front again.
Okay.
All right, can you see our recorded data from that experiment?
Yeah.
And how would we compare the cycle time or the period for our experiment 1 versus experiment 2?
Yeah, it looks like the period's a lot longer. when we went at a slower speed.
Okay.
And it also looks like the when you go around, it doesn't just drop like to go vertically one all at once. It sort of seems to slowly decline.
So how do you think the data would change compared to our first experiments if we had a larger planet here on our record player in our model?
My guess would be that the when it probably would dip even lower than it does with a bigger ball, with a bigger planet.
So, okay, so if our small planet is in front of our sun, you might not be able to see it, but it's directly in front of the star. The way we currently have it positioned, we're going from like 1200, 1300 lux, and then down to like 400, 500 lux. That's where our planet would be roughly if we're on the same orbit. And can you see the graph, the change in the graph?
Yeah, the graph is a lot lower now. It's like about 100.
Draw some comparisons or contrast. What seems to be the same or different from this photo and the example that we did?
Yeah, so the same. It seems like when there was the size difference like affected the lowest light intensity. So with the bigger planet, the light intensity seemed to like the minimum seemed to be a lot lower, and when there's a small planet, the minimum seemed to be about um, not as low.
Yeah, and how about can we see a period in this NASA photo?
It doesn't. I don't see. It looks like we just goes down and then continues. So um, I don't. You probably might need a little more time for a period, I guess. So no.
So in a real activity, if we're doing this as part of an assignment, you could answer the questions to all the questions here in the lab report, and you could put in your answer, and then I, as a teacher, would get to see any of this, but we won't make you do that. So if we're going to discover an exoplanet using this method, what does that mean for sort of the orientation of like our telescope and this distant solar system and the planet that we're trying to discover?
Yeah, so it seems like when you're trying to take some of that, find some data, you have to also like figure out how far you are away from the star to see like see like what it affects like how bright the star is and the intensity of the um, star, and then you have to.
The PocketLab is our telescope, and the light bulb is our sun. What happens if we happen to be pointed at a solar system and the orbit's going around like this?
Oh, and then that would be the light intensity might not change at all, maybe.
Yeah. So it seems like we have to get lucky that our planet, our star, and our telescope are sort of in line, that you can see this shadow effect when the planet is transiting in front.
Yeah, I didn't think about that. Yeah.
Yeah. So if we're even like, it doesn't even have to be completely perpendicular, but if it's like a little bit, just a little bit angled, and this is, remember, a giant planet in comparison to our star, we would miss that shadow that it's casting.
That's pretty. Sometimes I hear about like a planet is discovered far away, but if that means that they're not discovering a lot, then that's interesting. Wow.